Thank you all the organizer for this beautiful conference. I so far have enjoyed it very much. So I will want to so in contrast to Jennifer, I will not present proofs. I will try to do a lot of examples and actually will only near the end come to the large deviation convergence because I thought it might be good to understand a little bit more intuitively what's going on here. So in particular, already here in this example that left convergence does not imply right convergence. I want to come back to that for a moment. And I need some, actually I don't want to do that. I want to hide from you what I'm doing. Okay, so recall that we defined right convergent by this convergence of the log of the Homs. And now the counterexample Jennifer gave you was this cycle. Okay, so if we take the cycle on the odd numbers, you can't two-color it. So the Hom is 0, the F is minus infinity, and on the even colors, the log is 2, and the limit goes to 0. So it sort of oscillates. So it's clearly not convergent. But somehow this is a stupid example. Okay, why is it a stupid example? Well, first of all, you could just remove a single edge from this guy. Then you get a line. And on the lines, you can actually prove that this converges on all h. Okay, so that's one way to take care of it. And having a notion of graph limits where you have a nicely convergent sequence and then I add one edge and it's suddenly not convergent anymore. I mean, now I know we are sparse, but we're not that sparse that adding a single edge should really make a difference, right? So that's sort of nasty. And the second one is actually another question, namely, if you, instead of allowing sort of constraints, you put softcore H's, which Percy doesn't like, but if you do that, then again, this guy is convergent. And actually, if you would talk to a physicist, they would tell you, well, this right convergent is supposed to model some statistical physics systems, and while in principle you can think of hardcore as an idealization, there are no hardcores. I mean, if I bang them hard enough, they just are not hard anymore. And so hardcore should only exist at the limit of something soft going to hard. And it's a mathematical idealization of something. But if it's then true that for any softcore, no matter how sort of hard, but just not hard, it's true, then this seems to be not a good counterexample. It seems not to catch what we really mean. Okay? So just for notation, I don't think that people have defined really what a Hom in general is. So a softcore graph is a graph where all the weights are strictly positive. And so if edge weights and vertex weights, and this is sort of, why does it look so funny?
The term twisted is out of focus on the little bits to the side.
There are different parts I can make in focus, but I think this is just what it is. Okay, it's the drugs I took last night. So RV fed us, actually. So you have these weights which are strictly positive, and now what do? You sum over all homomorphisms, but depending on the color, sort of you have edge weights, so you take sort of all red vertices get maybe a factor 1/2, and all blue vertices get a factor 1/4, and all black vertices get a factor 5. And in a similar way, different edges get different weights, and this is actually, if you look at it, all of statistical physics. Okay, and then the right convergence on this graph H is defined as before. And now if some of the betas are 0, for example, if all the betas are 0 or 1, then you're back to the case Jennifer studied. Good. So now, so this still raises the question, are these two cases related? Okay? And in this case, I can sort of relate them to you in sort of a roundabout way. I can say the following. Well, let's think of the following. Okay, if I have a softcore graph, okay, what happens if I leave out an edge? Well, this factor will be So if I leave out the factor, these guys will vary between some largest number, let's say 1, and some smallest number, epsilon. So leaving out one edge in your graph G will just change this guy by a factor between 1 and epsilon. So it will change this log by a constant, which disappears in the limit. So clearly removing this one edge changes nothing in softcore. And then if I in softcore remove the edge, I could get sort of to this thing with this stretched out. How can I relate that to Z? So that's sort of the question. And to study that, I need a little bit notation, not much. Some of it I gave in my problem session on Monday. So one of them, let's call two graph sequences equivalent if they live on the same vertex set and they differ in less than number of n edges. You could probably also define them equivalent if the vertex set had a similar condition, but for this purpose, this is enough. Okay, so these are considered equivalent. And if you have a graph where some of the weights might be 0, just soften it up a little bit, put an epsilon. Okay, epsilon can be tiny, so it will be very near to the guy where there were 0, but maybe it's not 0 anymore. Okay, and now we have the following fact which starts to relate the two things. So the first thing is actually not that difficult. So what might we want to do? So we had this counter example, which maybe I want to put up. And so in this counter example, we removed one edge. And then suddenly the problem that we couldn't buy color anymore was gone. Okay? So you might want to say the following. Look at this free energy where the Hom is just the log of the Hom. And as you remove edges from G, okay, so you start with the graph Gn, and you now look at Gn prime and start to remove edges to get rid of this problem of zeros. Okay? So as you do that, this guy will clearly get larger and larger. And so the one problem you may ask, well, could it become too large? Well, it can never become too large if these edge weights are bounded, but that's sort of stupid. So can it? Well, it turns out it can never become larger than the limit epsilon goes to 0 of this softcore guy. Okay? So that's the first thing. That's not that hard to prove, actually. You can probably, if you think about it for a few minutes, prove it yourself. It's trivial for a fixed epsilon if you send and then you take epsilon to 0 by monotonicity. So this is not difficult. What is sort of, however, a little bit more difficult is to show that you can actually attain that. So there exists a sequence such that this lim sub becomes actually a lim and this inequality becomes an equality. So in other words, there are two possibilities. Maybe this limit epsilon goes to 0 is minus infinity. We call that convergent. Okay? So maybe actually after removing the soft core, before epsilon is 0, it's always a finite number, but it could go to minus infinity. If this is the case, well, then this is also minus infinity, there's nothing to prove. If this is not minus infinity, then what happens is that you can remove more and more edges from your graph Gn prime until actually you can't raise it anymore. And at that point, you have reached this limit. So it turns out that these hardcore constraints which gave us a counterexample are sort of not there. I mean, you can always remove enough edges from the graph such that they're just little o in the limit, and actually you get what should be the limit. Okay? So that now raises the question, is actually this counterexample, so maybe actually what we had here is not true anymore, because to prove that, we use this counterexample. Okay, so that is now the next question we want to look at. So I will define a sequence to be right convergent if it's right convergent on all softcore graphs. Okay? We just learned, forget about hardcore graphs. Well, if you like them, put them in, but you don't need to. Okay? Everything you want to learn, you can learn from hardcore graphs. Softcore graphs, yeah. So now, does left convergence now imply right convergence? Well, the answer is still no. So what is the counterexample? Well, let's look at the following. You take a sequence where for odd n, you choose a degree d regular random graph, and for even n, you choose a bipartite degree d random graph. And now if you look at the max cut in this graph, okay, then, well, in this case it's trivial, okay, it's d times n half. And in this case, it's not quite trivial. In expectations, n d over 4, and if d is large enough, it actually is not that much less or that much more. It differs by order of square root of d times n. Okay? So for large enough d, these two are really different. They're both large, but they're different. And that implies that we don't have right convergence. And why is that? Well, so now I'm not allowed to look at hardcore graphs anymore, so I have to take a softcore graph. Here it is. Okay, that's one of Vera's graphs. It's E on this edge in the middle and 1 on the two loops. And now, what is it? Well, the HOM is clearly bounded below by the max cut because I can take one situation. So if I can take one configuration which realizes the max cut. And I have only two colors at my disposal, so at most 2 to the n configuration. So this is an upper bound. And this max cut didn't converge. It was sort of d half divided by n and d quarters divided by n. And if d is large, this overrides the 2, and you will get not convergence. Okay? So what we have is actually that this theorem, this statement there holds. And we learned a little bit more. We sort of learned that so if I consider local this and global this, then this is clearly local by definition. Okay, but this is not quite local because the max cut is clearly something which is not local, so it has sort of some global part in it. So actually, this is sort of the first local global convergence we see in this talk. And actually, I think, and this one is the last purely local convergence you will see in this talk. Okay, good. So what do we do about that? Okay, we would like something maybe which is stronger than this one, or at least which sort of implies right convergence. And so let's go back to dense graphs. Okay, so we introduce a notion called partition convergence. So we would like to distinguish this bipartite and non-bipartite d-regular graphs. Is that a question?
Yeah, I mean, just to use example, background, for example, I mean, they're not based on a sort of parity obstruction or bipartiteness. I mean, if you exclude examples which, where the main obstruction seems to be parity or sometimes bipartite or not maybe, but...
Well, I mean, so if it's local structure, to some extent, right-left convergence captures the local structure. So you want probably some global structure to get a counterexample. So we'll see that. We'll go through more counterexamples, and maybe once we have run through all of them, we'll see whether you want more. So we find a topology which distinguishes these two. Okay, so let's go back to dense for a moment. So in the dense setting, we introduced a notion of what we called quotients at the time, but let me just tell you what it is. You take your graph G, you divide it into many groups, color them in different colors if you want, and now you measure how many edges are between red and green, blue and red, and so on. And then you define a weighted graph where the vertex weights are just sort of the proportion of the sizes. If you want the corresponding, you define a quotient which is just the Samaretti finite model of this partition. Okay, where the betas are the edge densities and the alphas are the relative size of the groups. Okay, and then we look at the set of all these, where you vary over all possible partitions. And then we proved a theorem which we probably at Lazzi sort of points out proved long before, but that's where we had it in a preprint, which I think is still, it will eventually appear this year at some point in the annals. It took a while to get through. But anyhow, what we proved there was that left convergence, right convergence, and that right convergence is actually equivalent to the convergence of this set of multi-way cuts. Okay? And as Vera said, it's actually very near to right convergence. And where right convergence might be sort of unusual for you if you're not a physicist, multi-way cuts should be something which should be very interesting for you if you're a computer scientist or a combinatorialist. So I think actually this right convergence is to some extent as natural as a left convergence, definitely if you're interested in this here. Okay? So the idea would be, well, just adopt this definition. If you look at it, this guy will not make much sense if you just literally take the definition over. So we have to adapt it a little bit. So how would we adapt it? And as I do that, I will tell you what we did in the other setting. Okay, so we look at some coloring of the graph with Q colors. Then we partition the vertex set into color classes. And now the sizes of the color classes will be one weight. And the number of edges between them will be another one. So this is the number of edges between green and red. And here you would normally divide something proportional to n squared, which will tend to 0 because the number of edges are linear. So instead, we divide by n. Okay, so we get some weighted graph. The quotients, I call it the quotient of G and this coloring, or of G and the corresponding partition. And then we can look at the set of quotients. And to some extent, it's a subset of R plus to the Q plus Q squared, Q for the Q vertex weight and Q squared for the Q squared edge weights. And some of them are equal, so it's actually a lower dimensional subspace. But anyhow, it's definitely a subset of this. And now we define partition convergence. Or actually, so all this actually Bela and Oliver realized, sort of not sort of the thing you want to do. And so they defined it to be partition convergent if for all Q, this set converges in the Hausdorff metric on subsets of R plus to the Q plus Q squared. By the way, you could replace R plus by 0 and the max degree in D because you can't never have more edges than that. So it's actually a compact subset. Okay? And now this clearly distinguishes these two graphs, because now one of them has sort of a max cut. I mean, the max, so if you now color with two colors and you make the two sizes equal, then you will see that in one case the support here will contain, I mean the support there should contain, it goes up to the max cut, and if the max cut is different, then these two sets are different. So this partition convergence definitely figures this out. Okay? So we have this partition convergence, and it's to some extent in this picture I drew before. This one seems to be very, was global red or blue? I forgot. Global, so this is global. Okay, and this is local. And this sort of in between. And now the question is, well, how are these classes related? Okay? So the first thing you might hope is, well, this was our problem with right convergence. Maybe it works. Well, if it really, I shouldn't have colored it yet, because if it implied right convergence is better, also has some local information. So now you guess that it won't. Okay? So if you look at partition convergence, so it turns out that partition convergence actually does not imply right convergence. In fact, it doesn't even imply left convergence. Okay, so this does not imply left convergence. And if it implied right convergence, then via this error, it should imply left convergence. Okay, so it doesn't do that. And this is a counterexample which is due to David and Lazzi. And the counterexample is as follows. Take as your sequence a union of 4 cycles if n is even, and of 6 cycles if n is odd. And, okay, add sort of up to 5 isolated vertices if it doesn't add up to n, which will not play any role in the end. And now, it's clearly not left convergence, right? I mean, this one has 6 cycles and this one doesn't. So, but it turns out to be partition convergent. So why is that the case? Well, if you look at these graphs, they're all degree 2 graphs. So it turns out that for degree 2 graphs, or more general for regular graphs, you can determine the weights of the vertices from the edges by summing over one of the components, and they sort of come in. If you want to relate it to the weights of the vertices, degrees come in, but if the degrees are all the same, they come in a trivial way. So there's one relation you must have. There's another relation you must have, that all the vertex weights add up to 1, because that's how it was defined. And it turns out that now you give me one of these, and I can actually just, now you give me some coloring which obeys these conditions, and then I can just color this bipartite graph by choosing one group. So I want to color red-blue, so I choose up to a certain number red-blue. Then I want to color blue-green, I choose up to a certain number here. And I can do the same thing here, and it doesn't really matter. Okay, fine. If I use here sort of 20, I have used 5 groups, and if I want here 20 vertices, I have used sort of 3 groups, slightly a little bit. But except for that difference, you see no difference when you want to color it in such a way that you match partitions, match cuts. Okay, so this is this. So what about maybe the other way around? So maybe this one seems to contain a lot of information. Maybe we can hope that it goes in this direction. Okay, so does right convergence imply partition convergence? Well, the answer is again no. Okay? So how do we now make our counterexample? Let's choose a sequence of graph which has a non-negligible min bisection. Take again your favorite random construction. Okay, some expander. Okay, so you have an expander, you have at least delta times n is your min bisection. Assume it's right convergent. If it's not right convergence, then you look at your set of weighted graphs, you approximate them by rational weights, and for each of them you sort of choose a convergent subsequence, and you do a diagonal sequence argument, and in the end your sequence is right convergent. So let's just assume it starts off right convergence. And now, so that seems not to be a contradiction. It's because, well, this guy might quite well be partition convergent. It is, right? But now I do something different. I construct Gn by, again, one of these parity tricks, which people don't like. So for odd n, I just choose the graph as it is. And for even, I choose 2 copies of the graph disjoint with half the number of vertices. Okay? Now, this guy has min bisection delta n, and this guy has min bisection 0. Okay, so this sequence is clearly not partition convergent, but it's right convergent. And why? Well, the homomorphisms from 2 disconnected graphs is just the square, it's a product of the homs. And now you take the log, you get the 2 down, you have n half vertices, it all nicely combines. They have exactly the same free energies. So it is actually right convergent. Okay, so we have actually that right convergence does not imply partition convergence. Which, if you go through these errors here, means that, I mean, you have no error here, which is sort of non-trivial. Because if you had one in this direction, then you could use this one. If you had one in this direction, you could this one. So the errors which are, I mean, in both directions, so you don't have any, these are all non-trivial subsets of each other. Okay? Good. Okay, so that's how far we got. So now I come to the notion of large deviation convergence. How am I doing on time? Oh, I have half an hour, I have tons of time. Okay? So we had that we colored this graph G with some colors and got these quotients which led to the notion of partition convergence. You can also do what Lazi talked about already. You can color the graph G with these colors and now look at the colored neighborhood distribution. Okay, so for each coloring you get certain cuts and you get certain, given, whenever I color it, I get some distribution of colored neighborhoods. And now I can look at these as the set of all of them. And then I can ask, do these sets converge on the house with respect to the Hausdorff metric on the corresponding, I mean, this is a certain dimensional subspace of R plus, or well, actually of 0, 1 plus, and this is a certain subdimensional subspace of 0, D, where D is the max degree, to some dimension. And we have the Hausdorff dimension, the Hausdorff metric on subsets. Do they converge or do they not? Okay? And this will define you the partition convergence and the colored neighborhood convergence, actually, and both of them Bela and Oliver introduced a few years ago. Okay? So, and it's in contrast to, so this picture is sort of very interesting because in the dense case, all of these were equivalent. Okay? So now we have two more, well, one more notion is this one, but let me also give you another one. Is the following. But you may want to say, you know, why we're always looking at these sets? We're really forgetting the statistics of these colorings. That may be too much information to throw out. Maybe it's a better idea to say, look, choose this sigma uniformly at random, and then look at the cuts as a random variable. Okay? And once you have random variables, you can ask, do they have a limit theorem? Do they have sort of does it converge to a normal distribution? Well, all these are not very good notions. What we really want to know eventually, we want to take things, take logs and divide by n. So we want to know large deviations. Okay? So I will here first put something up, and which my first page, I want to, where's my work? Yellow here. So if you are a mathematician, you will kill me because my definition is wrong. And if you are a probabilist, and if you're not a probabilist, you will kill me because this may really not mean anything to you. So let me do, but nevertheless, I will first do this with the wrong definition. Okay? So this sequence Gn will be called large deviation convergence if for all Q, this guy obeys the large deviation principle. So far, nothing is wrong. This means there exists a rate function IQ such that, and now this is actually not quite correct, but roughly speaking, what we ask is that you look at these guys, these are random variables, okay, these are certain cuts. You now want to know, I randomly color my vertices, what cuts do I see? And now I put in some set of cuts, where chances are that, I mean, you just have sort of a finite end, I mean, you have Q to the n many colorings, and there are a lot of cuts around. It's not that likely that actually this will exactly fit. So this may actually be very small, this probability. It's probably exponentially small. So let's take the log and divide by the volume. Okay? And then the second thing, I have here an infimum. Why do we have that? Well, the inf is a supremum outside the minus. And that sort of means if these guys are all exponentially decaying, then probably in the limit, the one which decays the least should matter the most. So that now I just explained what large deviation is about for the moment. Okay? Now, roughly speaking, let me formulate it differently. Roughly speaking, what this convergent means is that if you look at this uniform random coloring, but then you fix these cuts to be equal f, then you get an entropy which is log Q minus this guy. And how much you go down is exactly this, the log of this probability in the limit. Okay? Now, since this is a mass conference, I can't get away by not defining what I really mean. So now we define it correctly for those of you who care. So this is the large deviation in its full glory. So A should be any Borel. So F is some subset of 0, 1 to the Q times Q squared, Q plus Q squared. A is a Borel subset of it. It could be open, it could be closed. In general, it's neither. So A bar is the closure. A0 is the largest open set inside. Obviously, left is smaller than the right because we take this infim over more sets and there's a minus sign. And the large deviation principle says that, so saying that something has a large deviation principle with rate IQ is defined by that. That's a lim sup. So that the rate function on the open sets is bounded by the lim inf, is bounded above by the lim sup, which again is bounded by the rate function on the closed set. Okay? So this is what we have here. So our picture got a little bit more complicated. Now we have large deviation convergence, we have partition convergence, we have colored neighborhood convergence. This one was local, this was half local, this was clearly global, and this was half. Now, are there things which we can immediately say? Well, yes. So first of all, I claim that what is obvious is that this implies this. So why is this the case? Well, think of taking the balls of radius 1. Then for each vertex you see sort of the degrees into the other colors. And if you add up all these degrees, you just get the number of edges from red to blue. So actually, this is sort of clearly implying that. Okay? And it seems sort of, well, and actually if you look at some of the counterexample, if you do a look at the counterexample I just gave, you will see that you cannot, and also clearly implies this. Why is that the case? Well, choose just to color everything with the same color. Then you get sort of the set of distributions, but since there's only one color, you only get one distribution. So this distribution must converge. That's Benjamini-Schramm. And as Jennifer told you, Benjamini-Schramm is equivalent to left convergence. So therefore, since this implies both something global, something local, this is clearly both global and local. Okay. Now, a little bit more work, but actually sort of heuristically not that difficult to understand, is also that this should imply this. Why is that? Well, I'm looking at the entropy, how many sigmas are there roughly which have a fixed certain cut size, okay? Well, so I should in particular be able to tell whether there is one or not. Now you might say, wait a second, you're taking limits and stuff, maybe it disappears. But you realize that if there's at least one cut, then the probability there must be at least 1 over q to the number of vertices. And if you take the log, you get out a number of vertices and you will get a finite rate here. Okay? So you will see from which f's have finite rate, which f's will be realized in this set of partitions. So if you really want to do it, you have to do your epsilon argument, and it ends up being a few pages to write down, but it's sort of heuristically and it all has to do with the fact that large deviations look very simple, but then if you do the details, they're sort of a little nasty. But nevertheless, this we have. So at least it has a little bit of global. Okay? So now, there are two questions which arise. which is, I defined a notion for you. But it's sort of, I mean, it could, for example, be that we have this implication, but that actually there's no set of graphs which are large deviation convergent. And that's, well, obviously false. Just take a sequence of isolated vertices that will easily have that, because then you get independent colorings. And actually, if you take any sequence of, if you take any graph which is made out of the same finite blob repeated many times, then you get independent colorings on these blobs and independent random variables. I mean, finite space, everything could be as nice as, I mean, can't be nicer than that. And it's sort of a standard result that they obey a large deviation principle. And then once you have the distribution on these blobs, you can recalculate your cut. So that's not hard, okay? So a little bit more interesting is that actually the grid is large deviation convergent, okay? So, and how do you prove that? Well, what you do is you take your grid and you cut it in half. And now you see that the number of edges are sublinear and the number of vertices, the edges you destroy with that. But then the right and left are sort of independent, you can calculate things. And if you do that, you get something which is very similar to what you know from subadditivity arguments in proving limits. And I mean, to some extent, then you prove subadditivity of this entropy morally. Again, if you write it down, it's a longer proof. But morally, you prove subadditivity of this entropy, and you prove that actually this thing is large deviation convergent. Okay? So at least there are some interesting examples there. The next question is, does large deviation convergence imply anything else? And that's our last theorem. So this says that, in fact, it does. So large deviation convergence implies right convergence. And you can actually calculate it. So it turns out that this free energy is a supremum over what? So if you have if you fix the cuts, this is morally the entropy of the cuts. And this is how much a cut, the weight of a cut. The weight of a cut is e to the this times n. So let's see whether we understand that. E to the this will give you a beta ij of h to a beta ij of f. Does that sort of make sense? I claim it does. Why? Beta ij of h for, let's say, I red and j blue measures how much you pay for a red-blue edge. And now you raise this to the power beta ij of f times n, but beta ij of f times n was the size of the cut, so it tells you how many edges are there which are red to blue. So this should be roughly the factor which appears in these homes. And there's a factor 1/2 because, well, I sum over all I and j, and before I summed over all u and v, and I have counted edges double if I don't pay attention. So that's why I have the half. So, and again, to actually, this proof now starts to be, the proofs get nastier and nastier, but the heuristic is sort of relatively, so that's a heuristic. So we have that this implies this, and therefore this must also have, which in turn implies local, so it also must have some local and global properties, okay? So this is local, and this is global. So there's one more theorem which we sort of trying to prove. So the question, the open problem I asked was this. Okay, does the colored neighborhood convergence imply right convergence? I mean, that's what at least sort of in my head it was invented for. I mean, there's all other kinds of beautiful mathematics if you go into sort of the graphings and the stuff which is sort of introduced by Gabor-Elek and sort of now analyzed a lot by Lazzi and Balash, how these are related. So there is sort of other reasons why we might want to study this colored neighborhood convergence, but it would be really nice to know whether this implies this. On the other hand, we sort of have a feeling that this is actually slightly stronger than this, And so far we had sort of, I don't know, 5 or 10 proofs which all ended up not being quite correct. And the problem is that you can't really prove that directly. So you invent all kinds of other notions of convergence on the way, just like we did when we eventually proved all this equivalence in the dense setting. We actually didn't have all these notions. We just wanted to prove right is equivalent to left, but we couldn't. We had to go through the quotients and the delta and so on. So as you prove things, I think this theory of sparse graph limits, if one wants to prove this, maybe one has to invent a new version of, I don't know, super neighborhood colored convergence or whatever to actually get from here to here. I sort of would think that, I mean, if I should conjecture today, I would conjecture that this implies this and this implies this. But we have another idea here which is not dead. So, but these proofs are all such that when you write them out, they're only not dead once you write them out. Okay. Yeah? I see. Well, we have not really talked about, that's actually another whole topic which has not been studied that much here, which is sort of random. Okay, well, I take it back. Okay. Actually, this paper roughly 3 years ago, where these notions of partition and colored neighborhood convergence were invented, started by studying sparse random graphs. It just turns out that even for it turns out that in the dense settings, these sparse random graphs are very nasty and a lot of things, right? We don't, for example, we would probably conjecture that they're right convergent. But if you prove that, you prove a lot of other things. Some of the things which largely mentioned up there would, I think, imply that random graphs are right convergence, right?
Certainly, we would love to know whether they are colored neighborhood convergent or local global convergent.
So, and we would love to know whether they're large deviation convergent. I mean, it's, and nobody knows any of that. People have sort of chipped away little corners here, GN for certain ages. We sort of know if they are, David is here, he can probably tell us what is sort of the latest status, which GNP, for which ages is GN 1 over n convergent.
H is a weighted graph and it satisfies some convexity property in the sense that the matrix is a positive semi-definite in some sense. Then it's right convergent with respect to sparse random graphs. But that clearly is just a subset of all H's.
Right, and the other subset of H's is the one Jennifer mentioned. So if you take, oh, by the way, if you take hardcore graphs which obey the condition Jennifer had, then you can also, using the same method, show that, so in principle it could be that you take a hardcore graph, you take the limit, you soften it and you take the limit. The two limits don't have to be the same. Nowhere here did I say that they are the same. The only thing I said is that if you take the soft call, so assume you have a sequence of graphs which are hardcore convergent. I soften it, I take that limit. The two could be different. The only thing the theorem says is once you remove enough edges from the graph sequence Gn, they must be equal. I mean, there are simple examples where you take these odd cycles and you add sort of, you take the counterexample and then you add something which you can clearly color, and then you would get on some subgraphs it's 1/2, on the other it's 1, and then you can remove some that it's sort of that you only get one of them out. But if you soften it, you go back to what you should get. And so we don't know that. But this kind of stuff can't happen if the sparsity condition with Jennifer stated showed. So, but even for those, I don't think we know that it on GNP in general works, because these random graphs happen to not have bounded degrees. And we really need bounded degrees, a few degrees which are not, morally, obviously, it shouldn't matter, but we can't prove it. So, I mean, a lot of these things, so that's actually something which is really missing in this theory, more than a few examples, sort of, to really get a much richer set of examples. I mean, I think I more or less covered all non-trivial examples we know of. What do you think, Lazzi? I mean, some of these converge to trees or converge to your...
Yeah, I agree. I mean, there's random graphs, regular random graphs, and
grids.
Grids. And, well, I mean,
you could
grids are, and some of these are hyperfinite, so that's usually much easier to handle. Once you have expanded graphs, it gets very difficult.
Maybe a partial answer or a discussion on May's question is, I don't know if we have so many models that people use, even though there should be, so we can't even start to answer the question. We don't have natural classes of models for sparse graphs. I mean, we can make up some, but I don't know, you know, the exponential graph models are dense graphs, and I don't know a rich analog of that in the sparse graph case.
Right, I mean, the only ones we know are sort of this, you take sort of what used to be I mean, you can take any sequence of convergent dense graphs and now keep each edge with probability alpha over n. Okay, so that will become, but these graphs they're sort of cheating. They're very much like dense graphs. And I actually don't even know whether for those these things are known. Do we know colored neighborhood convergent if you...
I don't think so. I mean, that should be more difficult than for the GN.
Yes, that's true. Right, so I mean, we can come up with models which are more difficult than GNP, but we want models which are easier than GNP, which is sort of very unusual, right, for our community.
One other thing, you said you were going to discuss the question that was earlier. It does seem as if a lot of the examples are two different things stuck together, and it'd be interesting to ask if there was some way of natural families that fit together, whether the models or whether the limiting theory is different. You know, that somehow, for even and odd n, if you make...
So whether you have some kind of models, that's actually very interesting. If you say I have models which I sort of grow one from the other, so it's sort of the next one should be obtained by adding edges to the previous one. That's interesting whether, I mean, I sort of don't think that all of these will be the same, but it's interesting whether then some of these classes will collapse.
It's also somewhat related maybe to the question that Andrea Choka asked, which are the graphs, classes of graphs, for which every feature can be computed by a local algorithm. I mean, so whatever can be computed by local algorithm.
But not approximately, really.
I mean, approximately, yeah. I mean, you have to make the question precise, but probably random graphs, deregular random graphs have this property. So whatever relation you can compute on them, you can compute by a local, approximately by a local algorithm. You don't think so? Okay.
Take a vote.
Avi?
I just wanted to ask this question about examples that are different than grids and random. Because there are quite interesting groups, finitely generated groups, whose local structure is interesting. They have, their neighborhoods, their local neighborhoods are interesting, and they don't look like. I mean, they can be at the same time have lots of short cycles and be expanders or go slowly. So if you look just as a sequence, just Borgs around the identity, and then you get some, probably I would assume, convergent sequences that are interesting. That will probably be
There are some intruding
So you have a measure on the unit square. Where
You have a measure on the unit square. And now you keep ending at that point. And if the measure is really not bad, then this defines your permutation. There is an ordering here. There is an ordering here that gives you a random permutation.
you have a permutation.
Once you have a random permutation, you take D of that, take the union, that gets you an irregular random graph. This way you can get irregular random graphs or irregular random bipartite graphs if you put the right measure on the unit square. Okay, and then in between you get the continuous class of graphs.
So then we could have a counterexample where build it's not just even and odd, but sort of, so it sort of slowly goes to bipartite and back.
I don't think that anything has improved on this class in general. It's interesting to look at it.
So the question is, could you build a sequence of graph which is just growing and do the same? So where you start sort of with bipartite, now you add sort of more and more these edges until it becomes sort of, it looks like a totally random deregular graph. And then you sort of start growing and
This sounds very similar to me what David and Prasad and Bayati are doing.
That's right. Well, what we've done there was interpolating between graph with n nodes and two graphs with n over two nodes disjoint, which is slightly different. But I think that this discussion reminds me of something else in the coding theory, which is called the spatial code. That they managed to prove some better results in coding theory, which you can rephrase as problems on trying to solve some optimization problem, where they start embedding sparse random graphs into series, and at the beginning it's just one big random graph, and then starts having some spatial structure, and then collapses back into the original graph with larger number of nodes, and turns out that in between you obtain some bounds on the rate of decoding, which you could not have obtained for the original model. So it's still a little bit black magic for me how that works, but there is something in the coding theory that...
so would you conjecture I can build a sequence of graphs where I really sort of add vertices and edges in an organic way and get these counterexamples where they behave for, if the vertices have 2 to the n, if you have 2 to the n vertices, it behaves exactly like bipartite, and if I have 2 to the n plus 1, it behaves like, so that I slowly can go back between bipartite and non-bipartite, so that I get a counterexample where I don't really have this jumping from one to the other. It almost sounds as if we probably...
Other examples to what?
Well, the question was, all these counterexamples was for even graphs I do this, for odd graphs I do this, and people don't like this.
You could make it happening slowly.
You can make it happen slowly, and you could probably even make it such that it happens in some kind monotonely.
It's true, but I was asking for natural ways of doing it.
Yeah. You can take a semi-bipartite, semi-non-bipartite.
So we will, I think we should thank Christian
Thank you.
again.